Let's wait for 2 3 minutes. Then I will start. Okay, let me start. So check this video. Fine. Before starting the week 7 one, I just want to start with the last time what we have solved. Uh, I think this is the question. So there is some confusion somewhere. I remember. So here I have shown this thing, that is when I was using this partial the partial function here, that is ax square plus, sorry, the particular integral solution, we have assumed that as ax square plus cx plus d, corresponding to what? Corresponding to this particular equation, that is x square minus x, which is a polynomial. This is regarding the superposition principle for finding out the particular integral. We have found out the exponential one, but for the polynomial function, we haven't uh, really got into that. So we have assumed that yp2, that is for the polynomial, this is the particular integral function. And if you differentiate it once with respect to x, it gives you this. Second time, it gives you 2a. And you put it into the main equation because that is also the solution. So this is the main equation, d2y by dx2 plus dy dx minus 2y. And when you have put it, you will get something like this. And so the first one is fine, that is minus 2a is equal to 1, that is a is equal to minus half. And the next one, that is your 2a, this one, and the next one is your minus 2c. Yes, so this will be, uh, just a minute, let me just quickly see it. Yeah, so 2a minus 2c is equal to minus 1. This is another equation, definitely. And what about the constants? If you take 2a plus c minus 2d, so you can just write 2a plus c minus 2d is equal to, actually it is 0, right? And now here, if you just look into this, 2c will be equal to something like 2a plus 1, and 2a is nothing but 2 times minus half, because a we have already got minus half plus 1. So it's minus 1 plus 1, which is equal to 0. Therefore, C will come out to be 0. So all these things you can chalk out. There is some mistake here. Okay, I will re-upload this one. So this will give you C is equal to 0. Now, now if you put this particular equation for the constant, what you get is that your this becomes minus 1, fine, 2 times C. C is 0 now. Okay, and this is minus 2D. So you can clearly see that if you just cancel each and everything, so 2D will be equal to minus 1. So D will be equal to minus half. So what are the three things we have got? E is equal to 0, A is equal to minus half, and D is equal to minus half. Therefore, yp2 is ax square, that is minus half x square, minus half, because the cx is 0. So that's what we have put it here. Okay. So there is a mistake which I have done it here. So that is the issue, because you can see that clearly c minus a is not equal to 1. If you have to write it, it has to be equal to half. Then only it will, I think, uh, the right way of looking into it. Right. So yeah. So finally, this is what you have. Okay. So this is the mistake which we have done here. All right. So yes, fine. So this is what I wanted to show in the last class. I will re-upload this part and you can check it. Fine. Let's come to now the week 7, the contents of the week 7. So this is week 7 problem solving session on the course mathematical methods in physics 1. Right. So this particular week's lecture is particularly designed for giving the concept of Laplace transform, right? This is the Laplace transform. So Laplace transform, we have already seen one of the transforms, which is nothing but the Fourier transform, where we use the complex integrals like e to the power the something minus iota s x, or minus iota e to the power minus iota omega x or something, right? But in the Laplace transform, we will define and we can also use this Laplace transform. In fact, we can use Fourier transform also to solve the differential equations, like ordinary differential equations. So the main thing is that to solve different ways to solve the ordinary differential equation. So the basic ways we have seen, that is find out the complementary function and the particular integral function, and that is also, we have two ways we have seen, right? In the last class, we have seen that there is a superposition principle also, through which the particular integration becomes easier to calculate, right? So that is another thing. But Laplace transform is also widely used for solving the ordinary differential equation. Maybe by the end of the class, I may not show the ordinary differential equation, how to solve it, but we will discuss about the Laplace transform today. Maybe touch upon the inverse Laplace transform. There is an extra class possible in this particular Saturday, 3 to 5 p.m. So there we will complete this part and try to see that how the inverse Laplace transform is calculated, and we can find out the solution of the ordinary differential equation using Laplace transform. That is the major goal. Okay, so let us first define what is Laplace transform and what is the use of this Laplace transform. The use of Laplace transform is in electronics, analog electronics, where you have operational amplifier, right? You have a differentiator circuit, you have an integrator circuit. There you generally use, since it is easy to represent uh, any time domain stuffs into the some Fourier domain or Laplace domain. Okay, so transform means from one domain to another, it is being transformed based on a particular integration function or like that. Okay, so how this Laplace transform is defined? Let us start. So it says that if f of some t or x, whatever you wanted to say, f of t be a function which is defined for all positive values of t, then f of s, okay, f of s is defined as 0 to infinity f of t e to the power minus st dt. This f of s is actually called the Laplace transform of the function f of t. We denote this as L of f of t, which is nothing but your f of s. So s is the variable in Laplace domain. Okay. Generally, in electronics, when we use this Laplace domain, that is S, that is defined as S is equal to minus iota omega or something like that. Like the omega is the frequency, angular frequency in electronics. Okay, so you can see that this particular integral, this Laplace transform, is transforming a function which is in time domain initially, or time or any space domain. From that, it is again changing into a frequency domain, just like a Fourier transform, but its integration is done from 0 to infinity, whereas in the Fourier transform, as we have seen, it is generally done from minus infinity to infinity. Correct? So this is the only difference which we can find. Okay, so this is the definition of the Laplace transform. So let us now, based on this particular definition, let us now calculate the Laplace transform of different functions. Okay, so let's calculate. So I would say calculation of Laplace transform of different functions. All right. So the first one, which we will talk about, is, let's say, what will be the Laplace transform of 1? So 1 is also a constant function, right? So how we can find out the Laplace transform of 1? Just go to the basic definition what we have seen, which is f of t e to the power minus st dt. Okay, so let's try this. 0 to infinity, this is the Laplace transform. F of t is 1 e to the power minus st dt. All right, so this gives you, if you integrate it, e to the power minus st, it will come out to be e to the power minus st as it is divided by minus s, right? Whatever is there with the t, because with respect to t it is being integrated. So with t, whatever is there will come in the denominator. This is the property of the integral. So 0 to infinity So what will happen? E to the power minus infinity is 0 minus e to the power minus 0 is what? 1. So it will be minus 1 by s. So ultimately it comes out to be 1 by s. So Laplace transform of 1 comes out to be 1 upon s. Okay. The next thing, so this is one of the functions which we have calculated. The next thing is that let us say Laplace transform p to the power n, some x to the power n, some kind of a polynomial function. There, what will you do? So, okay, doesn't matter, 0 to infinity. Follow the definition, e to the power n, e to the power minus st dt. This is the definition, we know. See, now this particular integral can be solved in different ways, but the best way to solve this kind of integral is using gamma function. Using gamma function. Okay. Now, what is a gamma function? Well, I can define it. Let's say gamma, this is how it is represented. Gamma of some n. N is some number. Okay? It can be fraction also. So gamma of n is defined as 0 to infinity t to the power n minus 1 e to the power minus t dt. Okay, this is gamma of n. Remember, when in the 0 to infinity integral, you have e to the power n minus 1, you get gamma of n. And this gamma of n is actually n plus 1 factorial. Alright, so these are the two basic properties. Okay, two basic properties, or I would say definition, whatever you want, of gamma function. Okay, so these are the few properties of gamma function. So why I am trying to say that I will calculate this integral using gamma function? Because look into the definition of the gamma function. See, it is exactly of the similar fashion as this, right? So we can easily use by some kind of transformation or substitution, we can easily make this integral to this, and then we can easily get the values. So let's do that. Okay. So let us write s of t, s into t is equal to some y. So s dt will be equal to dy, right? So dt will be equal to dy by s. And what is y? I'm sorry. What is t? Y by s. All right. So now put this into this particular integral. So what will happen? See, the limit will not change, because if you put t is equal to 0 here in this equation, you put t is equal to 0, y will be 0. If t is infinity, y will also tend to infinity. So the limits will not change. That is another interesting part. Okay. T to the power n, I know t is y by s. So it is y to the power n divided by s to the power n. E to the power minus y, because st we have defined as y. What about dt? Is dy by s. All right. So okay. S is a constant quantity because this integral is with respect to dy. So I can take this s to the power n plus 1 outside, and we can have 0 to infinity as it is y to the power n e to the power minus y dy. Can we calculate this from the gamma function? Because if you look at the definition of the gamma function, yes, instead of n minus 1, I have n. That's the only change, right? So what I can do is that this n, so will be equal to some n minus 1. Therefore, what we will get is that you will get this integral as gamma of n plus 1. Why? Because you have gamma of n when you have n minus 1, right? So if you add a plus 1 with it, if you add a plus 1 with it, then what will happen? It will be t to the power n. That is exactly what I require. So here also you have to add 1. So it will be gamma of n plus 1. All right. So this is what you have. So now what is gamma of n plus 1? We have seen that gamma of n is, I'm sorry, I have made a mistake here. This is actually n minus 1 answer. This is n minus 1. Okay. So gamma of n plus 1 will be nothing but n factorial. Okay. Gamma of n is n minus 1 factorial. Gamma of n plus 1 will be n factorial. Therefore, the result, that is L, Laplace transformation of t to the power n, will come out to be n factorial divided by s to the power n plus 1. This is the Laplace transform of t to the power n. So we have seen the Laplace transform of 1, which is 1 by s. For t to the power n, using gamma function, we have tried to substitute this particular integral, and we found out that the value of t to the power n Laplace transform is n factorial upon s to the power n plus 1. Fine. Next is the third part, which is Laplace transform of, let's say, exponential at, some exponential function with a times t. How to do it? Simple. 0 to infinity, e to the power at, e to the power minus st dt. This is the definition, and we will follow the definition. So it will be 0 to infinity, e to the power, let's say take minus common, so s minus at dt. So what will be the final result? E to the power minus s minus a t divided by s minus a with a negative sign. And it will go from 0 to infinity. So this will be 1 upon s minus. So when you have e to the power at, you will get 1 upon s minus a as the Laplace transform. Very interestingly, when you have function 1, you have got 1 by s. Remember, 1 by s. But now, when you have exponential at, it is 1 by s minus n. So it's a kind of a shifting, you can see. Fine. This is the third function. Let's say the fourth function. Now let us try with the cosine and sine functions. So let's calculate the Laplace transform of cos of at, some value which is multiplied with the t. Again, going by the definition, 0 to infinity, cos of at, e to the power minus st dt. Okay, so what will you do in this case? I know that to simplify the integral, I know that cos at is nothing but e to the power iota at plus e to the power minus iota at by 2. This is the definition of the cosine function, right? In terms of exponential to the power iota. So just put that 0 to infinity e to the power iota at plus e to the power minus iota at divided by 2 into e to the power minus st dt. In the next step, we can write this 0 to infinity e to the power minus s minus iota a times t divided by 2 dt plus 0 to infinity e to the power minus s plus iota a t by 2 dt. These are the two things which we get. And we know we have solved this integral lot more times. So half, it comes out to be 1 upon s minus iota. So whatever is there here, that will just come down. So this is plus 1 s plus iota. All right. So further, if you solve, you will get. So we just have a multiplying these two. So it becomes s minus iota, s plus iota, and taking the LCM. So you have s plus iota a plus s minus iota a. That brings you that this iota a will cancel. So you get 2s divided by 2. Now this becomes a square plus a square. Why plus? Because iota square is minus 1. So when you have iota a whole square, you get a minus sign extra. That makes it negative, negative, positive. So 2, 2 cancels. So Laplace transform of cos 80 comes out to be s divided by a square plus b square. Important result. Okay. Similarly, we have done it for cosine. Let's do it for sine. So Laplace transform of sine 80, that will give you 0 to infinity sine 80 e to the power minus st dt. All right. So what we will do? We know that sine of 80 can be written as e to the power iota 80 minus e to the power minus iota 80. But in the denominator, you have, instead of 2, you have 2 iota. Okay. So just put this and solve. You will get the result 0 to infinity. I will solve it step by step. So e to the power iota 80 minus e to the power minus iota 80 divided by 2i. Okay. And into e to the power minus st dt. All right. So now what we will do is that let's take 1 upon 2i common out of the integral 0 to infinity e to the power minus s minus iota e t. There is no t, 2 here. Okay. And you have minus 1 upon 2i integral 0 to infinity e to the power minus s plus iota e t dt. All right. So now what we will do is that we'll solve this integral, and we know the result of these integrals we are doing for the couple of times now. So we know this will come out to be, when you put the integration limit, it comes out to be s minus iota a minus 1 upon s plus iota e. So finally, take the LCM of both, which will be the multiplication of this s plus iota e. So it becomes s plus iota e minus s plus iota e. So s cancels out. So in this time, unlike the earlier case, it becomes 2ia divided by a square, again plus a square, because you have iota. So now this 2 iota will cancel. This gives you the Laplace transform as a upon a square plus a square. So the difference between the cos and the sine Laplace transform is that in one case it is s upon a square plus a square. On the other hand, for the sine, it is a upon a square plus a square. Fine. So these are the two important points. Now there are certain functions which are the hyperbolic functions. Uh, so let me just write. So some hyperbolic functions are there. For example, you have cos hyperbolic x or sine hyperbolic x. So how will you write this? So cos hyperbolic x is nothing but cos of iota x. Okay. Instead of cos x, I am writing cos of iota x. So what is the definition of cos? We have just now seen. So e to the power iota times iota x plus e to the power minus iota times iota x divided by 2. Right? This is the definition. So just put it, iota square becomes minus. Again, iota square becomes minus, this becomes plus divided by 2. So cos hyperbolic x is e to the power x plus e to the power minus x divided by 2. Alright. Similarly, for sine hyperbolic x, we generally define it as minus iota times sine iota x. This is some different definition. So again, so what about sine iota x? We know that it is e to the power iota times iota x minus e to the power minus iota times iota x, sorry, okay, divided by 2i. All right, so it becomes e to the power minus x minus e to the power iota square minus minus plus x divided by 2. Okay, so now what we have to do is that, so this is sine of iota x. Okay, but we have to multiply with minus iota in order to get the hyperbolic function. So it becomes minus iota e to the power minus x minus e to the power x divided by 2i. So I cancels, negative can be multiplied inside. So e to the power x minus e to the power minus x divided by 2. So this is your sine hyperbolic x. Okay, so this is your sine hyperbolic x. This is your cos hyperbolic x. Simple definition compared to the actual function, right? So we will use this and try to find out the Laplace transform of the hyperbolic functions. Okay, so let's do it and then we will see, maybe move for the next part. Okay, so up to what number I give? So at 5. So the sixth one is about the Laplace transform of cos hyperbolic, let's say 80. So the definition remains same, 0 to infinity. So cos hyperbolic 80 e to the power minus st dt. Simple rule is that put the definition of cos 80 here in terms of exponential and then solve it. That is becoming easier. So 0 to infinity, cos hyperbolic can be written as e to the power 80 plus e to the power minus 80 divided by 2 into e to the power minus st dt. All right. So what we can do now? So 0 to infinity, e to the power minus s minus at plus e to the power minus s plus at, all right, dt and divided by 2. Okay. So now if you do the integral, you get half. The first integral becomes what? E to the power minus s minus a t divided by minus s minus a, and you have to take the limits from 0 to infinity plus e to the power minus s plus at divided by minus s plus a from 0 to infinity. That's all. So finally, after doing everything, it comes out to be 1 upon s minus a plus 1 upon s plus a after putting the limits. So again, further solving, it comes out to be, it's a kind of a square minus b square kind of a thing. And if you do the summation, then it comes out to be s plus a plus s minus a. So a cancels out. So it gives you 2s divided by 2 a square minus a square. So 2 cancels out. This gives you s divided by a square minus a square. So the basic definition of cos 80 and cos hyperbolic 80 is not much, but only the sign in the denominator. Otherwise, it is same. Same s in the denominator, but in the, sorry, in the numerator. In the denominator, you have a negative sign in between a square and a square. Whereas in the cos function, it was a plus. Right? So this is the basic difference. Similarly, if you do the, and let's do it actually, the Laplace transform of sine hyperbolic 80, which is easy to solve, just following the definition, 0 to infinity, sine hyperbolic 80, e to the power minus st dt. So writing it in terms of the exponential function because makes it easy, e to the power 80 minus e to the power minus 80 divided by 2 e to the power minus st dt. So you get 0 to infinity e to the power minus s minus a t by 2 dt minus 0 to infinity e to the power minus s plus a e dt divided by 2. So finally, if you solve it, it comes out to be half 1 upon s minus a minus 1 upon s plus a. All right. So you get what? Half. So if you take the LCM, you get s plus a into s minus a, which is same s square minus a square. But in the numerator, you get s plus a minus s plus a. So SS goes now, it comes out to be 2a divided by 2 a square minus a square. So 2 cancels out, you get a upon a square minus a square. So therefore, the Laplace transform of sine hyperbolic at will be a upon a square minus a square. So the only difference between the sine and the cos and the sine and the cos hyperbolic functions are that numerator remains the same as the actual function's Laplace transform, but in the denominator there is a negative sign between the square terms. Alright. Okay. Hyperbolic functions can be tan hyperbolic, cot hyperbolic, many others. Okay. Every thing we can do it. But let us stop here for the time being because we have calculated some basic functions which will be utilized. Now for other things, we will use several properties of the Laplace transform. So the next topic which I will cover here is the properties of the Laplace transform. And when we discuss a particular property, we will try to solve a question corresponding to each of them. So that will clear our concept and yeah, we can solve also. Fine. Okay. So just a minute. Okay. The next part is the properties of Laplace transform. So what are the properties of Laplace transform? The first property, you will see that it is just an integration based property. If you know the properties of the integrations, then you will be seeing that this property is exactly similar to that. So what it says is that if you take a Laplace transform of something like this, function a f1 of t plus b f2 of t, so there are two functions which is multiplied by a coefficient and added. In that case, your you can write this thing as a times L of f1t, right, plus b of L of f2. So you can see that it follows a kind of a superposition principle, right? So that is what is the major thing, and you can prove it very easily. So if you just take the left hand side, which is the Laplace transform of this particular function, that is a f1t plus b f2t. So if you do that, so what will happen? So you take 0 to infinity here, and you put the function a times f1 of t plus b times f2 of t, right? And put the e to the power minus st dt because that is the definition of the Laplace transform. So we are just putting it. That's all. So what we will do is that just allow the properties of integral to play a role. So the second step will be to take a and put 0 to infinity f1 of t e to the power minus st dt plus b 0 to infinity f2 of t e to the power minus st dt, right? and this is nothing but e into Laplace transform of f1 of t plus b into Laplace transform of f2 of t. So this is what your RHS is, right? So this is what the first property of the Laplace transform. The next property is also known as the shifting property. Okay, so this is the shifting property of Laplace transform. So it is the shifting property, and you can see the shifting property is that if you take a Laplace transform of e to the power at f of t, you get something like this f of s minus a. So we have already seen that whenever we have used e to the power at, if I just show you, we have derived it. So when we have done, see, e to the power at, the Laplace transform of e to the power at, we have found it as 1 upon s minus a, right? So the important factor is that when we have taken Laplace transform of 1, it gives you 1 by s. But immediately when this 1 is multiplied by e to the power at, you get the Laplace transform of e to the power at, which is 1 upon s minus a. So you can see it from here also that it will be something of the order f of s minus a, some function in the Laplace domain of s minus a. So how to prove it? Very easy. So you take the left hand side, and left hand side is the Laplace transform of this part, right? So let's do it. So it is 0 to infinity e to the power at f of t e to the power minus st dt. And you can see that there is an exponential function here, there is an exponential function here. We will reduce it to one exponential function, that is f of t, that is e to the power minus s minus a t dt. So instead of now writing e to the power minus st, we are writing it as s minus a into t. So this we can write it as the some function of f of s minus a. Right? We can write. So this is what we are writing. Okay. So this is nothing but your RHS. All right. So this is called the shifting property. Fine. Okay. Let's take an example of this and try to solve it. Okay. One example let me give you. Let us say the function f of t is of the order or of the form e to the power say 7 by 2 e to the power 5t. So you can see that the function f of t, some function of f dash t suppose, is multiplied by exponential of some at, right? So immediately we know that its Laplace transform. So if this f dash t, if it is having the Laplace transform of f of s, then I'm sorry, if it has a Laplace transform of f of s, then e to the 5t f dash t, its Laplace transform will be f of s minus 5. All right, this is what we are trying to show here, and that is what we will be applying. So f of s minus 5 should be the thing. So let's focus on this part, the f dash t. So let us find out the Laplace transform of f dash t. And what is this f dash t? So f of t, we are writing it as f dash t times e to the power 5t, right? E to the power at something. Okay, and this f dash t is what you call as t to the power 7 by 2. That's all, right? So now, if you take the Laplace transform of f dash t, which we are calling it as some f of s, that will be what? Go by the definition, 0 to infinity, e to the power 7 by 2, e to the power minus st dt. All right, this is fine. So, what will be the result of this? See, again, we can reduce this into, we can solve using gamma function. This is a very powerful technique using gamma function to solve an integral. I have already shown some uh, application of the gamma function as I was mentioning, the definitions. Okay, so the next step will be therefore, let y be equal to st. Similarly, t will be equal to y by s, dt will be equal to dy by s. Limits will not change. Okay, so yes, that's all. So 0 to infinity, the limits are not changing. Y to the power s by 2 divided by s to the power 7 by 2. Okay, and what else? You have e to the power minus y dy by s. So we know, right? So why we are doing this all process? We don't require to do, don't need. Why? Because we have already seen, we have already seen that Laplace transform of e to the power n is what? N plus 1 factorial divided by s to the power n plus 1. Just write that. So Laplace transform of t to the power 7 by 2 will be equal to what? 7 by 2 plus 1 factorial divided by s to the power 7 by 2 plus 1. Okay? And okay. Now, if you say that 7 by 2 plus 1 factorial, how do we calculate? You don't need to calculate. 7 by 2 plus 1 can be written as gamma of gamma of your, I'm sorry, just let me just show you where from I am calling this C. Okay, this is C. This is n factorial upon s to the power n plus 1. Let's go to now the bottom. So we have wrongly written the formula. So the formula will be, instead of this, the formula will be n factorial divided by s to the power n plus 1. We have already derived it, right? So it will be 7 by 2 factorial divided by s to the power 9 by 2, right? 7 by 2 plus 1. Question is that what will be the n factorial? I have already told you that gamma of n plus 1 is equal to n factorial. So 7 by 2 factorial can be written as gamma of 7 by 2 plus 1. And this is also a property of gamma, that you can write gamma of n plus 1 is equal to n gamma n. Okay, so you can write this as 7 by 2 gamma 7 by 2. All right, we can further reduce it. Can I write it like this? Yes. So what it will be? 7 by 2 into 5 by 2 into gamma of 5 by 2 can be written 3 by 2 plus 1. In this way, we can continue. 5 by 2 into 3 by 2. Further, we can write as half plus 1. So we get 7 by 2, 5 by 2 into 3 by 2 into half, gamma half. And we know that gamma of half is equal to root 5. So finally, therefore, Laplace transform of t to the power 7 by 2, that is f dash, comes out to be 7 into 5 into 3, which comes out to be 105 divided by 2 to the 4 to the 8 to the 16 into root 5. All right. So this should be the answer. Okay. But divided by, of course, the s to the power 9 by 2. But we need Laplace transform of t to the power 7 by 2 e to the power 5t. So what we will do? Nothing. See, change this by 16, whatever it is. This will be s minus 5 to the power 9 by 2. That's all. This should be done. This is the shifting property. Using shifting property. All right. That's all. Okay. So this is the answer. Fine. Let's. We can take another example to solve an integral. Let me check. Okay. Let's take another example. Maybe it is not. So we can use the property of the Laplace transform in this particular question. So question is that find out the Laplace transform of sine 2t sine 3t. So it is a multiplication of two sine functions, sine 2t times sine 3t. Okay, no problem. So what we will do is that in the first step, we will first write sine 2t in terms of exponential. Iota 2t minus e to the power minus iota 2t divided by 2i, right? Into sine 3. That's all. Now you can clearly see that there is an exponential term here and there is a function here. So can I write this as some f of t and this as some exponential function? So this becomes the shifting property. This is heading towards the shifting property. Okay, so what I will do is that I take 1 upon 2 iota, which is a constant quantity for time being. So L of e to the power iota 2t sine 3t minus L of e to the power minus iota 2t sine 3t. That's all. So you can clearly see that shifting property can be applied. All right. So we can go further. So 1 upon 2 I keep it as it is. What will be the shifting property? You already know what is the Laplace transform of sine 3t. So Laplace transform of sine 3t is what? Is 3 times or 3 over. Okay, let me come here. So Laplace transform of sine 3t we have already seen is a upon, so 3 upon s square plus 2 square, right? Which is 9. In this case, what will happen? We have to use the shifting property. So instead of s square, we will have s minus iota times 2 whole square plus 9. Correct? This should be the thing. Similarly, here it will be 3 divided by s plus 2i whole square plus 9. Alright, this should be the thing. That is what is the power of the properties of the Laplace transform. Just in one step, you can skip all integrals and finally find out this kind of an expression. Okay, 3 is a constant and is common, so 3 upon 2i we can take it outside. And the next steps are just only solving this part. That's all. So what we will do? So it will be 1 upon, let's open this bracket. So it will be s square minus 4, okay, minus 4 is I plus 9 minus 1 upon s square minus 4 plus 4 is I plus 9. Okay, so this is the next step. Further, you can write 3 upon 2i. And what next? You can just take this s square minus 4 is I plus 5 s square plus 4si plus 5. All right. So in the numerator, it will be the square plus 4si plus 5 minus a square plus 4si minus 5. So what will happen? A square, 5 cancels. You finally get 3 upon 2i, 8si divided by, you can clearly see that one a square plus 5 is there and there is a 4si part. So you can just write this as x square plus 5 whole square plus 16 is square. Okay, then 2i, this can go to 4s. So it will be, the next step will be to have 12s divided by, you can open this further, s4 plus 25 plus 2, 5, 10 is square plus 16 square, which can be further written as 12s divided by s to the power 4 plus 26s square plus 25, which we can solve it somewhat quadratic equation kind of. So 12s divided by a square plus 25 into a square plus 1. This is the answer. So how we have solved this? Very easy. Take t is equal to s square. So you get in the denominator t square plus 26t plus 25. You can write t square plus 25t plus t plus 25. So t plus 25 plus 1, t plus 25. Take common t plus 25 into t plus 1. And this is what exactly we are writing here. Okay, so this is how you can skip integration steps, complex integrations, and easily write an expression of the Laplace transform. So this is the usefulness of the properties of the Laplace transform. Now there are many other properties which will come one by one, and based on that we will try to solve the questions. Okay, so the next couple of things are easy and we can easily solve them. Okay, so let's try one by one. The next important property is number 3, is the Laplace transform of the derivatives of a function. Okay, Laplace transform of the derivatives. Now, why this property is very important? The property is important because, as you can see, we are trying to calculate the Laplace transform of the derivatives. And you know that in the ordinary differential equation, ODEs, we have differentials, right? Bdx, b2, dx2, all these things. So if we know how to calculate the Laplace transform of the derivative, when we try to solve the ordinary differential equation using Laplace transform, it will be easier. So this is very fundamental for solving the ordinary differential equations. Okay, just a minute. Fine. So Laplace transform of the derivatives. So the property says that Laplace transform of, say, first order derivative f dash t is nothing but s times Laplace transform of f of t, okay, minus f of 0. So this we can write L of f t can be written as f of s minus f of 0. This is what the Laplace transform is. Now how to prove this? Simple. L of f dash t first order derivative. So it will be 0 to infinity. What it will be? F dash t e to the power minus st dt, right? Just solve it by parts. You get e to the power minus st. F dash t's integral will be f of t from 0 to infinity, all right? Minus, you have the derivative of e to the power minus st, so it becomes plus, okay? And you have an s e to the power minus st and f dash t dt. All right. So this will be the next part. So what it will be there? If you put infinity, this becomes 0. E to the power minus s infinity will be 0. But if you put 0, it will be only f of 0. All right. Plus. So you have, okay, so with a minus sign, of course. Okay. On the other hand, you have s which can be taken outside because this integral is in the form of dt. Okay. Another important thing is that we have missed. There is another integral f dash t dt times dt. So because by parts, so let me again write it. It will be easier for you. So the by parts definition is that you first write e to the power minus st as it is. You have this f dash t dt from 0 to infinity minus you have ddt of e to the power minus st integration f dash t dt from 0 to infinity from 0 to infinity. So here what will happen? It will be e to the power minus st ft because it is already f dash t. Now you have the integral. So you have to 0 to infinity. Okay. Minus. Okay. Remember this integration limit will be open everything. And this becomes plus s 0 to infinity as it is e to the power minus st f dash t, which can be written as ft. Okay, so this is the thing. So if you do it, infinity if you put, it will be 0. So it will be minus f of 0 plus s, and this is what? The Laplace transform of. So s fs minus f of 0. Okay, so this is your Laplace transform of the derivative. This is first derivative. But if you do similarly, if you perform second order derivative, that is what you require because for the ODE you don't need to get too much higher orders. Okay, we perform second order derivative. So you get L of f double dash t will be equal to s square f of s minus f dash of 0 minus s f 0. Remember, this is important and please remember this. Okay, s square, of course, you can see that this integral will be twice. So it will be s square f of s minus f dash of 0 minus s into f of 0. That's the thing. Okay. So this is an important property we must remember, particularly for the solving the ODE. Okay. Fine. Let's go to the fourth property. The fourth one. The fourth one is Laplace transform of integral. Okay. Laplace transform of the integral. So how to do it? So Laplace transform of the 0 to t ft dt. Okay, this can be written as fs of s. That means what is fs? Fs is the Laplace transform of f of t. So if you have a function which is being integrated from 0 to some time t or some variable, some I would say value t, then if you know the Laplace transform of ft, the actual function, just divide by s, that will be the value of the Laplace transform of the integration of the function. Okay, now how to do that? Well, how to prove it? So let us say that something, let's say chi of t, some function chi, which is a function of t, is say 0 to t ft dt. All right. Now chi of 0 is say 0. Okay. So now chi dash t is nothing but 0 to t f dash t dt. Now we know that Laplace transform of chi dash t is nothing but s times Laplace transform of chi t. Okay. So Laplace transform of chi dash t means if you take a derivative of this, what will you get? So this becomes nothing but the f of s, and this gives you s times Laplace transform of chi t, which is nothing but the integration of 0 to t f t dt. Clear? So you get f of s divided by s as the Laplace transform of 0 to t f t dt. That's all. So chi of t is the integration. Chi dash of t is actually chi dash of t will be nothing but f of t. That's all. When you have an integration, if you differentiate it with respect to time, it will be f of t only. So Laplace transform of chi dash t is nothing but Laplace transform of chi t. Sorry, ft. So that is what you are getting. Okay. So in that way, you can prove it. Fine. And let me give you another property, which is we will prove this. So the Laplace transform of say t to the power n into f of t can be written as minus 1 to the power n dn dsn of f of s. Again, remember f of s is nothing but Laplace transform of f of t. So if you know a function whose Laplace transform is required to be found out, and it is like this order, then separate out the function and t to the power n. That function's Laplace transform is f of s. Take the nth derivative of that, multiply with a minus 1 to the power n. You get the actual Laplace transform. So how will you get that? How will you prove this? We'll start from here. So dds of fs is what? dds of the Laplace transform 0 to infinity f of t e to the power minus st dt, right? So dds is differentiating with respect to s. So this will be differentiated. So first time if you differentiate, what will happen? So inside the integral 0 to infinity, you will get the minus t, ft of course, e to the power minus st as it is dt. Similarly, if you do d2 by ds2 fs, then what will happen? It will be 0 to infinity. Again, there will be a multiplication, so it will be minus t whole square ft e to the power minus st dt. So if you now do it similar way, dn upon dsn of fs, so what will happen? So it will be 0 to infinity minus t to the power n f of t e to the power minus st dt. Alright, this is what you will get. Fine. So can you take this minus 1 to the power n outside and 0 to infinity e to the power n ft e to the power minus st dt. So minus 1 to the power n, keep it as it is. What is this? Laplace transform of e to the power n ft. Okay. Now, on the other side, you have dn f of s upon dsn. Now, this minus 1 to the power n, if you just divide it here, so it will become minus 1 to the power minus n dn upon dsn of fs, which is nothing but Laplace transform of e to the power n ft. And if you have a minus 1 and to the power, you can either write minus n or plus n. It does not matter. It is exactly the same as minus 1 to the power n dn dsn of fs. That's all. Okay. So this is what you have. Fine. So this is your uh, what you call as your property, the fifth property. Now we will solve some questions that will use these properties, and we will see that what will be the how we can simplify the Laplace transform of certain things. So let's try out some questions. So find out the Laplace transformation of t sine 2t. Okay, you can clearly see it is something like t to the power n times f of t. So what is your f of s? Is Laplace transform of f of t. So I am writing this as Laplace transform of some t to the power 1 f of t. Can I write? Yes. But Laplace transform of f of t is what? Laplace transform of sine 2t, which is a very known function. That's why we have derived. So it will be 2 divided by a square plus 4. All right, this should be the thing. Now, you know f of s. Now, then what is the Laplace transform of t into sine of 2t? Is nothing but once you differentiate dds of 2 upon s square plus 4, and you have just multiplied with a minus 1. So minus 1, so it will be what? dds of 2 upon s square plus 4. Just try to do it. It is minus 1. So it will be s square plus 4 to the power minus 2 with a minus 1, and there is a 2 as it is into 2s. Alright. So minus minus gives you plus 2 2s are 4 s divided by s square plus 4 whole square. This should be the answer. See, in just 2 3 steps, we can easily find out the value of the Laplace transform. But if you try to do it with integration, you will definitely get it. But it will be a complicated process. That is what is I am trying to convey, that properties of Laplace transform you should apply. Whatever you know, whatever the properties we are going through, you should apply into the question so that you can make it easy and fast. Okay, this is one of the questions. The second one is a combination of too many things. Look at it and see how quickly we can approach this kind of a question. So Laplace transform of, I am saying 0 to t e to the power minus 2t t sin t dt. This is what you have to solve for. Look, there are a couple of things which are there. I am seeing three things, right? One is that, first of all, there is an integration. Okay, there is an integration. And we know that for the Laplace transform, the integration is if integration function gives you fs by s. Great. Second thing which I see is the first thing. Second thing which I see is e to the power minus 2t sin t, which is showing you the shifting property. All right. So that will be f of s minus a or whatever you want. Okay. Third thing is some t is being multiplied by some function f of t. So that itself has another property. So three things are combined here and try to put into this particular question. So what we do is that for the solution, we take the integration as it is and put the e to the power minus 2t sine 2t sine t dt this together. Okay. So this becomes now my f of t. Great. No problem. So can we find out the Laplace transform of f of t? We can. So Laplace transform of e to the power minus 2t sine t. Okay. How we can write this? Laplace transform of sine t we know, which is 1 upon a square plus 1. Alright. This is for the sine t. But Laplace transform of e to the power minus 2t sine t will follow, apply shifting property. Shifting property to this, you get 1 upon s plus 2. Remember, we have e to the power at and we write as s minus a. So now you have minus, so it will be plus. This plus 1. That's all. This is the Laplace transform of the ft, which is the shifting property e to the power minus 2t into sin t. Great. This is done. So this becomes your f of s. Excellent. So now you have 0 to t, t times f of t dt. Let's do the Laplace transform of this because we can write this as, right, the Laplace transform t into f of t. So how to do that? So Laplace transform of t into f of t is what? So you have dds with a minus sign of fs. And what is that? Minus dds of 1 upon s plus 2 whole square plus, I'm sorry, uh, plus 1. I'm sorry, plus 1. Okay. So what it will be therefore? It will be minus minus will be plus 1 and it will be 2 times s plus 2 and you have s plus 2 whole square plus 1 whole square. Right? This should be the answer. And then you have to take the integration of this. Right? And so if you know that this function is supposed capital Ft, okay, so we are actually writing the Laplace transform of integration of capital Ft dt, which is nothing but L of Tft divided by S. So just put an S. Okay, so it will be 1 by S, I would say. Just put this. So simultaneously, if you just put, it will be finished. That's all. This should be the result of this particular question. So you can see that these things are being applied here, and you can easily get a solution. Right? Complicated question having three functions together. First, use the shifting property and find out the f of s. Then, based on the f of s, you can calculate the Laplace transform of t f of t. Why do you require it? Because you want the 0 to t integration of the actual function. So, for the actual function, you need a Laplace transform. And for that, we have used this to finally divide it by s, which is the property of integration. So, dividing by s is property number 4. Right? That's all. So, we are using, yes, used property 2, 3, not 3, 2, 4, and 5. Of course, 1 may be useful, but yeah, that's all. So this is what is a very interesting question, as you can see. Fine. Okay. Let's go ahead for the unit step function and periodic function, how we calculate the Laplace transform. Then for the periodic function, we can solve a question. Then we will see how convolution is theorem is there, and we can solve it using Laplace transform. And then we can go for the what you call as the inverse Laplace transform if the time permits. If it's not, then we can cover it in the extra class on the Saturday, 3 to 5. Okay, let's go to the unit step function. This you can say as a property, or you can say that it is a particular case. Okay, so you can say this is the property like the unit step function. First of all, what is this unit step function? And then once you understand that what is the unit step function, its Laplace transform becomes very, very easy to calculate. Okay, so what is the unit step function? So unit step function is defined as u x minus a, which is nothing but 0 and 1. 0 when it is x is less than a and greater than equal to a, it becomes 1. So how it looks like? Very simple. If you draw it on a graph, you get something like this. You have your x, this is suppose your f of x. This is suppose x is equal to a. From here, it jumps to unity and continues till infinity. Okay, so this is 1, the value magnitude is 1. Fine, so this is your unit step function. So how to perform the Laplace transform? So what is the Laplace transform? So Laplace transform of unit step function, that is L u t minus a, suppose now I am writing, will be nothing but e to the power minus as divided by s. How? Now you just put the definition, u t minus a e to the power minus st dt. Alright. So I know from 0 to a, this is nothing but 0. But from a to infinity, this is 1. So which integral we should follow? This is 0. So you don't need to follow. This becomes e to the power minus s t divided by minus s from a to infinity. At infinity, it will be 0 minus, and this becomes e to the power minus as divided by minus s. So this gives you e to the power minus as divided by s. That's all. This is how it has to be done. All right. Fine. Now, what else we can do here? Fine. So let's go to the periodic function, seventh one. As we have seen in case of Fourier transformation, it requires a periodic function, right? For Fourier series, Dirichlet condition, a periodic function is required. And most of the times, or solving some physical problems, we see that some periodic functions is best, right? So can we find out the Laplace transform of a periodic function? So let's see. So periodic function. We know what is the periodic function. We have defined it. Okay? So periodic function. So if your f of t is a periodic function with a period t, then Laplace transform of f of t, which is a periodic function, gives the 0 to t instead of infinity, it becomes e to the power minus st f t dt divided by 1 minus e to the power minus st. This is the Laplace transform of a periodic function, how it comes. Okay. So now we will try to see how we can derive this. So we will go step by step and try to figure out how to find out the Laplace transform. Okay, fine. So let's go ahead. Okay, we know that Laplace transform of f of t, by definition, it is nothing but 0 to infinity f of t e to the power minus st dt. Right? This is the definition we are going through using that. Now, what I will do is that we'll divide it into several periods. Like 0 to t is the first period, where I am writing the function f of t e to the power minus st dt. The next period, like t to 2t, it will be e to the power minus st. The function's value will be the same in this dt. Similarly, and so on. Okay. Now what I will do is that in the next step, we'll write 0 to t, f of t, e to the power minus st dt as it is, plus 0 to, yeah. So what I will do is that 0 to t, same e to the power minus, only thing is that this t now becomes some t plus u. I'll come to it why it becomes like this. It becomes t plus u. Okay, dt. So what exactly is happening is that for the periodic function we know f of u plus some t will be nothing but f of u plus 2t and so on, right? Exactly that is what we are trying to see here. Okay. So instead of this t, it will be capital T. I have used some dummy variable instead of the small t. Okay, and capital T is the period. Similarly, 0 to t, again e to the power minus u plus 2t, f of u plus 2t into du. It's not now, yeah, this, and so on. Go ahead up to nt. Fine. So instead of t to 2t, we are just converting it into same 0 to t and converting this as this kind of an integral. Next step, 0 to t, if t is fine, e to the power minus st dt plus. Can I take, okay, this here, e to the power minus st common? Yes. And then 0 to t, e to the power minus su, f of u, du, right? Then plus e to the power minus 2st, 0 to t, e to the power minus su, fu, du, and so on. Okay. So finally, what I get is that 0 to t, e to the power minus st, ft, dt, okay, into 1 plus e to the power. See, these are the dummy variables, the u. You can convert every time this u as t. small t. So u can be visualized as small t. So it will be nothing but this plus e to the power minus 2st and so on up to infinity. It's an infinite series. So what will happen there? So it will be 0 to t e to the power minus st f of t dt, and this becomes 1 minus e to the power minus st. That's all. This is the Laplace transform. PNC. Okay, so just using the periodic function. So u can be t also. Okay, just replacing it. So this is how a simple proof of the periodic function Laplace transform can be derived. Okay, so let's do one question of this Laplace transform of a periodic function. Just by you can look at that by seeing the formula, you will just put it and you will get the result. Okay, so let's try that. So the question is find the Laplace transform t of periodic function, and as you know, periodic function whenever it is mentioned, its period will also be given. So f of t is say e to the power t in 0 to 2 pi. Period is mentioned. So the Laplace transform of ft I need to find out, and I know that for a periodic function it is 1 upon 1 minus e to the power minus s into t. T is 2 pi, correct? So we do this 0 to 2 pi e to the power t, the function e to the power minus st dt. All right, and then it's simple. So it will be 1 upon 1 minus e to the power minus s into 2 pi, 0 to 2 pi e to the power minus s minus 1 to dt. So 1 upon 1 minus e to the power minus s into 2 pi. This integration is minus s minus 1 t divided by minus s minus 1 from 0 to 2 pi. Okay, so just put this integration limit and you have your answer 2s pi, and you have so e to the power minus s minus 1 into 2 pi divided by minus s minus 1, and when you have 0, so it will be plus 1 upon s minus 1. So finally it is 1 minus e to the power minus s minus 1 to pi divided by s minus 1, and you have your 1 minus e to the power minus 2. Right. So this is what you get. Fine. So this is the answer. Fine. The next thing which we will talk about is convolution theorem. So the biggest property of convolution is like the convolution theorem. If you look at, so convolution is another, I would say, a mathematical technique to solve many things. Particularly, it is used in many parts like of the physics, like in applied physics, like geophysics. You find that convolution is an extremely important tool to do certain uh, geophysical calculations. So, so the important thing about convolution is that if you have to do a convolution for which you know what will be the definition of the convolution, which is integration based definition. But if you transform it into the Fourier domain or say Laplace domain, if you just multiply those Laplace transformed functions you will get the convolution in the original domain. Okay, so I will show you that. So about the convolution, which is very important property. So let me show convolution theorem. Okay, and I will show that how the Laplace transform is used. So suppose you have f1 of t and f2 of t, two functions, and corresponding to this, the Laplace transform of f1t is f1 of s, and the Laplace transform of f2t is f2 of s. So this is the Laplace transform. All right. So you can write further like this, that L of f1t is f1s and L of f2t is f2s. All right. So if you have a Laplace transform 0 to infinity, f1, say, okay, let us write it this. The definition is that I'm writing it in terms of x. Okay. So f1x, f2 t minus x. It's based on some parameter t, and you have to integrate with respect to x. This is the definition of convolution. This is the convolution definition. So you can see that it's an integration based definition. Okay. Now this Laplace transform of this is actually f1 of s into f2s. So what does it show? It shows that in the original domain, like time domain or space domain, if you perform a convolution, you have to calculate entire thing. But if you take a Laplace transform of this and find out the f1s and f2s, if you just multiply, if you just multiply these two Laplace transform functions and then take the inverse of this, you get the actual convolution. So that's the power of the convolution or the Laplace transform. Okay. So if we take Laplace transform of f1, f2 as that is f1s and f2s and multiply, and then take inverse Laplace transform, we get the actual convolution. Okay, so this is what makes it very interesting. So how to prove this? Simple. You take 0 to infinity, another 0 to infinity for the two Laplace transforms. So f1x, f2 t minus x e to the power minus st dx dt. So if you do this, I just quickly write it down: 0 to infinity f1x, f2 t minus x e to the power minus s t plus x minus t or minus x dx dt. So you get 0 to infinity f1x e to the power minus sx dx, 0 to infinity f2 t minus x e to the power minus s t minus x d. Let's say t minus x is some z, tt will be equal to dz. So if you do that, you can clearly see that there is an f1s here and there is an f2s clearly. Okay. So this is the proof. Okay, so this is the proof of the convolution theorem. Fine. What are the applications of Laplace transform? So in analog electronics, you use op amp, so differentiator integrated circuit. This is used. Okay, so that's all about the application and about the Laplace transform. So this completes the Laplace transform. We have discussed so many properties of the Laplace transform. Okay, so we still left some about 10-15 minutes. So we can start discussing about the inverse Laplace transform, because in solving the ordinary differential equation using Laplace transform, you not only require a Laplace transform of the functions, but you also require an inverse Laplace transform in order to get the solution. Okay, so let's list down some inverse Laplace transform. Okay, inverse Laplace transform. So what is the concept? Simple. If L of the Laplace transform of a function f of t is f of s, then L inverse of f of s is nothing but f of t. This is the part. We have seen in the Fourier transform and the inverse Fourier transform exactly similar way. This is how it is done. So L inverse is the inverse Laplace. Okay. So we have seen different. So we have found out the Laplace transform of several functions, right? From the beginning, we have seen functions. Okay. So based on that, we can easily write the inverse Laplace transform of certain functions. All right. So what are those? Number one, Laplace inverse of 1 by s. What is that? We have seen that Laplace transform of 1 is 1 by s. The Laplace transform, inverse Laplace transform of 1 by s will be equal to 1. This is the first. Second is Laplace inverse of 1 upon s to the power n will be what? Will be t to the power n minus 1 divided by n minus 1 factorial. Why? Because we have seen that n factorial upon s to the power n plus 1 is nothing but Laplace transform of t to the power n. Just based on that, we can write this. So, from better to write here. Okay, let me first write the list and then I can show that from where is it coming from. Next, 1 upon s minus a, some kind of a shifting property, right? So it will be e to the power at simply. Fourth, L inverse of s divided by s square minus a square will be nothing but cos hyperbolic at. Fifth, L inverse of 1 divided by a square minus a square is 1 by a, because a is a constant, right? So we can write like this. Sixth, L inverse of s upon s square plus a square is nothing but cos 80. Seventh, L inverse of 1 upon a square plus a square is 1 upon a sin 80. Alright. And last, let us look at L inverse of fs by s is nothing but 0 to t ftd. All right. So these are the eight properties or the eight list of the inverse Laplace transform, which we can directly write from where. So how is it coming from? So from where is it coming? So from where is it coming? So it is coming from the first one is coming from Laplace transform of 1 is nothing but 1 by s. This is coming from what? Right? So L of t to the power n is nothing but n factorial divided by s to the power n plus 1. All right. So if you put n minus 1, n as n minus 1, so put n tends to n minus 1, you get this exactly same. Next, third one is coming from what? So Laplace transform is easy. E to the power at comes out to be 1 upon s minus e. The fourth, this is simple. Cos hyperbolic at gives you s upon s square minus a square. This is also Laplace transform of sine hyperbolic at is a upon a square minus a. This is Laplace transform of cos at is s upon a square plus a. This is Laplace transform of sine at, which is a upon a square plus a square. And finally, Laplace transform of 0 to t ft dt is fs by s. Okay. So these are the couple of things which we can write. Okay. And there are other also. There are other also. I can mention another. The ninth one is that in inverse we have seen the integration one. Let us say the differentiation one. SFS. What it will be? It will be d dt of f of t plus h0 into delta t. Okay, because actually it is SFS minus f of 0. So you can write like this. So it's kind of a Dirac delta or Kronecker delta. Okay, so from where this is coming from is also easy. This is coming from Laplace transform of f dash t is nothing but SFS minus f0. All right, so this is from where it is coming. Let's see whether we can have any other things. So we can list it down. Let's see. L inverse of, okay, we can discuss this because it will take some time. Okay. Okay. So let's, okay, we have some 5 6 minutes. We can quickly do one question from the properties to find out the inverse Laplace transform. So one of the question is that, say your f of s is 3s minus 8 divided by 4s square plus 25. What is the inverse Laplace transform of this? So inverse Laplace transform. Okay, this is what you have to find. Simple. So you write it like this. So your f of s is nothing but 3s divided by 4s square plus 25 minus 8 divided by 4s square plus 25. Fine. F of s, 3s, can I take 4 outside and gets you s square plus 25 by 4 minus 8. Again, 4 can be taken outside, s square plus 25 by 4. All right. Next, f of s Can we reduce it down to 3s by 4 s square plus 5 by 2 square? Yes, we can. Minus 2 divided by s square plus 5 by 2 whole square. So we have to make it in such a way that we get a similar form of, say, some 1 upon a square plus a square or a square minus a square, right? So this is what the trick requires for the inverse Laplace transform. So you have a 5 by 2 here. You have a s here. You don't require to do any change. So 3 by 4. So now I can write L inverse of x, not required. Let it be f of s. Can I write this as s upon s square plus 5 by 2 whole square? Yes. But here we require it. See, there is a 2. Can I multiply by 5 by 2 and divide by 5 by 2? And then write s square plus 5 by 2 whole square. Okay. Now if you do the L inverse of this, that gives you d by 4. What is this? Cos of 5 by 2t minus. So this becomes 4 by 5 sine of 5 by 2. That's all. This is how the inverse Laplace transformation has to be calculated. We can further do another question and finish this today's lecture. So the next question is that find the Laplace inverse of 1 upon 4s plus 16 upon 1 minus s square. So how to do that? Simple. L inverse 1 upon 4s plus L inverse 16 upon 1 minus s. Alright. So 1 by 4 s. You can take 1 by 4 outside. So it will be L inverse of 1 by s plus L inverse. Look at this. 1 upon 1 minus s square. So what we can do is that, can you do it like this? We can. Yes. So 1 by 4. L inverse of 1 by s. What it will be? Just t or 1? 1. Because Laplace transformation of 1 is 1 by s. So this is 1. Minus 16 you can take out. So L inverse of 1 upon s square minus 1. This is a very known expression. So 1 by 4 minus L inverse of this can be written as sine hyperbolic t. So this is the answer. Alright. Now we will discuss some more properties and try to finish the inverse Laplace transform. So, so we will see more properties for inverse Laplace transform. Number one. Number two, we will use both Laplace and inverse Laplace transform for solving ODE. Okay, so these two things we will do it on Saturday if the class is there. Okay, or otherwise next Tuesday. Okay, and then finish the week 8 content, and that's all. We will be done. Okay, so today we have discussed many properties of Laplace transform and inverse Laplace transform. And in the next extra class on Saturday, 3 to 5, we will try to see the inverse Laplace transform properties and try to solve for the ODEs. So with this, I would like to end today's lecture. Thank you.